Good morning, folks. This is Mike coming back at you with another video on precalculus. In the previous video, we talked about solving exponential and logarithmic equations, the different types of equations we can have, and how we solve those guys. In this video, we are going to go back to that natural exponential function, e to the x, and we're going to see how it is involved in exponential growth and decay. The exponential function is heavily used in modeling real-life phenomenon. We're going to talk about a few samples here. In general, these real-life applications that we're going to see here use the following model. Y equals y naught times e raised to the kt, where y naught is the quantity at time t is equal to 0, k is a constant, and y is the quantity at any time t. Now, what dictates whether this is exponential growth or decay is all based on what that k value is right here. If k is positive, then the model that we would have shows exponential growth. If k is negative, then the model shows exponential decay. So the first case where we typically use an exponential model is in population growth. So here's an example. And in all three different real-life applications that we're going to see here in this video, it's really all, in essence, the same types of couple or so questions you could see. You're only either solving for that constant k, or you're finding some particular time or something like that. Could be something even easier than that too. But there's really a couple or so different types of questions that I can really ask you between these three real-life applications. So in the year 2000, the population of a country was 72 million people. In the year 2015, that same country had a population of 93 million people. If time t is measured in years since the year 2000, find the rate of population growth for this country. Based on this model, what will the population be in the year 2020? And let's just assume that this country had 0 cases of COVID-19. Had to bring a little bit of humor into this course somehow involving this crappy pandemic that we're in. So hopefully that worked. But again, we're going to set up that basic model of y naught times e raised to the kt. Y naught, as we said, is the quantity at time t is equal to 0. Well, here, time is measured in years since 2000. So if t is 0, then it's 0 years after 2000, or the year 2000, and we know the population of this country in the year 2000. It was 72 million people. So when I set up my model, I can substitute in for that y naught there. And I can just substitute in the 72, the sort of implication being that here population y is going to be in millions of people. So I need to find my rate of population growth. That is to say, I need to find that constant k. So how can we find k? Well, we're also told that in the year 2015, the same country had a population of 93 million people. This is giving us a piece of information, specifically a t value, and then a corresponding y value that we can use to figure out what is that k value. The year 2015, 15 years after the year 2000, obviously. So t is equal to 15, and when t is equal to 15, the population is 93 million, or in this case, 93. So I can make these substitutions into my model, and I find that 93 is equal to 72 times e raised to the power 15k. I'm going to begin by dividing both sides by that 72. I have to do that first, and you'll see why. So if I divide both sides by 72, I get 1.29167 is equal to e raised to the power 15k. Now, note that I rounded to several places here. Because we are going to be doing further calculations with this, you want to round to many, many places out so that your final answer is not impacted that much. For this early on, I would say no less than 5 places out would I round to. I need to solve for my k. K is in the exponent. This is an exponential equation, specifically a type 1 exponential equation. We solve these guys by converting to logarithmic form. When you convert it to logarithmic form, you get the natural log of 1.29167 is equal to 15k. You can figure out what the natural log of 1.29167 is. Just plug that into your calculator. To solve for k, divide both sides by 15. And we find that our k value is 0.01706, or as a percentage, it's going to be 1.706%. So that is the rate of population growth for this country, 1.706%. We then had to estimate what the population would be in 2020 minus the COVID. So we take that k value that we found, we substitute it back into our model, and now we get the full thing. 2020 is obviously 20 years after the year 2000. So if I substitute in 20 for t, I'm going to get this guy right here. Exponent is 0.3412, and rounded to, I rounded to 2 decimal places. You get approximately 101.28 million people. I would specify round to the nearest 10th or nearest 100th, something like that. But obviously, the more complicated of these two parts was coming up with our k value. Once we found the k value, estimating the 2020 population is just plugging in a value for t. Nothing crazy happening there. The next example is radioactive decay. Radioactive substances, radioactive isotopes, and half-lives. The half-life of a radioactive substance is the amount of time that it takes for half of the amount of your radioactive substance to break down and decompose and just no longer be there. So here's our problem here. The half-life of a particular radioactive substance is 355 years. Let's determine the decay constant K. So again, we are going to be working with that basic model, y equals y naught times e raised to the power kt. Now, just upon reading this question, it may seem like we don't have enough information to figure out this k value, but actually we do. It says the half-life of a particular radioactive substance is 355 years. So what we know is after 355 years, the amount of radioactive substance we have is half of what we started. Well, the amount we start with at time t is equal to 0, obviously, is y naught right here. So I know that when t is equal to 355, my y value is equal to 1/2 my starting value, or 1/2 y naught. So that is the key piece of information that we need to help us solve for k here. So as we just said, y of 355 is equal to 1/2 times y naught. Therefore, 1/2 y naught is equal to y naught times e raised to the power 355k. There's that key piece of info that we need. Now, continue on. I'm going to divide by the y naught first, and the y naughts disappear. I now have yet another type 1 exponential equation. To solve this, again, convert to logarithmic form, and you have natural log of 1/2 equals 355k. You can find natural log of 1/2 by plugging that into your calculator. Just take that number and divide it by 355k, and you get your decay constant, k, which is approximately negative 0.00195. So some questions, they may seem really tricky. It may seem like you don't have all the information that you need, but you actually do. Specifically with this type of question, it just comes down to really knowing what does it mean for some time frame to be the half-life. Moving on to our third and final real-life application of the exponential function here. This is a little bit of a review of something that we talked about earlier on in this chapter, but we're also going in a little bit more detail. We're all familiar with the concept of compound interest, and I mentioned the famous formula A equals P times E raised to the RT, where P is the amount of money you initially deposit, and R is the annual interest rate as a decimal. So here you go. You deposit $12,000 into a savings account with an annual interest rate of 4%. How many years will it be before your balance reaches $20,000? Now, just as a small side note, if you find a bank that's going to give you an annual interest rate of 4%, take it right away, because nowadays interest rates on savings accounts are, as you know, basically jack shit. So 4% is amazing. So I know how much I put in to start with, $12,000. That's my P value here. I know my annual interest rate, given as 4%. As a decimal, though, it's going to be 0.04. And I want to know what T value I need such that when I plug it in, I get $20,000 as my balance. So we want to find, as we said, the T value such that y of t, if we go back to the typical model, or in the famous formula, it would be a of t. And that would equal $20,000. So 20,000 equals 12,000 times e to the 0.04t. I'm going to start by dividing both sides by that 12,000 out front, and that gives me 5/3 equals e to the 0.04t. Again, type 1 exponential equation, again, convert to logarithmic form. Natural log of 5/3 equals 0.04t, and then divide both sides by 0.04. And you get approximately 12.771 years. So again, I might specify round to the nearest whole year, or nearest quarter year, or nearest half year, whatever. But it'll take approximately 12.771 years for your account balance to reach $20,000. So between these three real-life applications, we've really seen the only 2 or so types of problems I could realistically ask you to solve. You're either finding a specific t value, or you are finding your constant k, what really dictates whether it's exponential decay or exponential growth. Something I do want to just comment on, because we also did talk about logarithmic functions as well. Sometimes growth cannot last forever, and sometimes it has to level off at some point. And in this case, when we have this case where growth has to level off at some point, we use a logistic growth model in these cases. What does this thing look like? It looks like f of t, my apology there, f of t is equal to c divided by 1 plus a times e raised to the power minus bt. The function itself contains the natural exponential function in it, but there is, if you go on to take higher level math courses, there is a logarithmic piece that plays into it, but in a different context. And in this model, f of t has a horizontal asymptote at that height c. In some contexts, this is the carrying capacity. We could be talking about, say, predator-prey systems, something like that. There's many other areas. This is a kind of thing you would talk about more in, say, a differential equations class. So if you're going to go on to take differential equations, then you'll probably see this guy coming back up there. And just as an example of one other instance where this could happen, where growth cannot last forever and it has to level off at some point, the number of people who are infected with an illness, COVID-19. Yeah, so this is one more model that we could use to sort of model the growth in the number of people who contract some kind of illness or something like that. But this concludes our video on exponential growth and decay. In the next video, we're going to start a new chapter, and we're going to begin talking about trig. If you have any questions or comments, guys, please be sure to reach out to me. Postcards, shouting very loud, long-distance phone calls, message from the Postal Service, whatever. Until the next video, take it easy.